This is a battery made from 18650 sized lithium ion cells, and I made this battery here on this very bench. And today I'm going to do something very dangerous. I'm going to do something on the internet that other people are very, very good at, and I'm not very good at, and I'm going to make a video of me doing it, and I'm going to post that video on the internet. That's the video that you're watching right now. I'm going to take you through the steps of building, speccing, etc. this exact, well, another one just like it, 18650 lithium ion battery pack. And y'all are going to tear me apart for all the things I didn't do right. And that's okay. That's the process. I'm Joshua Bardwell. You're going to learn something today. The most interesting part of this video is going to be the physical construction of the pack, where I actually spot weld the nickel strips to the cells and solder the cells together and all that fun stuff. But before we can get into the physical construction, we have to buy the actual cells. And in order to do that, we have to know the specifications of the pack that we're going to try to build. And there are three main specifications that we're going to deal with. The first is the voltage that the pack needs to output. The second is the milliamp hours or capacity of the pack. And the third is the amount of current that we're going to need to pull from the pack. Let's start with voltage. And the voltage that we need the pack to provide depends on what we're going to be plugging the pack into. Every appliance, every load, everything that you plug a battery into has a certain voltage range that it expects. In my case, the intended use of this pack is going to be for powering goggles and other kinds of, maybe plug in a quadcopter on the bench, but mostly I just want a big chunky pack that I can run my goggles off of, that I can maybe run a phone charger off of, something like that. Not like a pack that I'm going to be using to fly a quadcopter. And the good news is that the voltage range of those appliances is typically very wide. A typical voltage range is 2S to 6S voltage. What does an S mean? S refers to putting the individual cells in series. And what you need to know about series wiring is that in series, the voltage of the individual cells adds up. A single cell, a 1S battery, has a voltage range of 3.0 to 4.2 volts. A 2-cell or 2S battery doubles those numbers, 6.0 to 8.4 volts, and so on, up to 3S, 4S, 5S, and 6S. And the good news is that that S count is going to actually tell us directly how many cells we need to buy. I think, though, that 6S is a little bit of overkill. This commercial pack from GEPRC is 6S2P. And so if we look here, we can kind of see the outline of 1, 2, 3, 4, 5, 6 batteries by 2P. So there's 12 cells in here. And that's just a little big. When I put that in my pocket, it's really pulling on my waistband. It's taking up a lot of space. I don't actually need that high voltage because, like, if you look at the voltage range of a set of FPV goggles, it's typically 2S or 3S at the bottom and 6S at the top. So I think a 4S battery is going to be just about perfect for this application. And as far as the parallel rating, let's talk about that. The capacity, or milliamp hours, of the battery determines how long the battery will run. This is a 6,000 milliamp hour battery. And we'll learn the exact milliamp hour rating of the battery when we go and start purchasing cells. But what you need to know is that the capacity of the battery increases as you add parallel groups. So this is a 4-cell battery. There's going to be 4 cells in series, and that's going to give me some number of milliamp hours. Let's say those are 3,000 milliamp hour cells. Well, if I had 4 cells in series, with one parallel group, just 4 cells in series, that would be a 4S 3,000 milliamp hour battery. That's how it works. If I wanted to increase that to get more runtime, I could add a parallel group. I would end up with a 4S 2P battery, and that would be 3,000 plus 3,000 equals 6,000 milliamp hours. And I could just keep doing that until the battery was so big and unwieldy that I didn't want to use it anymore. This here is a 4S 1P battery. And you can see here that it's got 1, 2, 3, 4 cells in it. And just take my word for it, those 4 cells are wired in series. And I know from experience that when I run my my FPV goggles off of a battery like this, it runs down faster than I would like. So I think 4S 1P is not going to cut it for me. I think 4S 2P is going to be just about perfect. And that, in fact, is going to give us a battery that looks like this. It's just a little bit smaller and a little bit lighter than a 6S 2P. The voltage is down in a range that's going to be a little more comfortable. For some things maybe aren't going to quite like running off of 6S, so I can run 4S stuff. Most everything will run off of 4S. This, I think, is the pack that we're going to go for. Now it's time to go start looking at actual cells that we can purchase. And in order to do that, I'm going to go to this website, 18650batterystore.com. This isn't the only place on the internet that you can buy lithium-ion cells, but it's one of the best ones in my opinion. I really like it. And the first decision we have to make is whether we're going to use 18650 or 21700 cells. These are two different sizes of cell. An 18650 cell is 18 millimeters in diameter by 65 millimeters tall, 18650, and a 21700 is, yes, you guessed it, 21 millimeters in diameter and 70 millimeters tall. So the 21700 is a little bit bigger, and as a result, it's going to have a little bit taller, a little bit more capacity. Since we're not really that concerned about weight, I mean, I'm a little bit concerned about weight, but mostly I want these packs to run for a long time. I think we're going to go with 21700s. So I'm going to click down here on 21700 batteries, and I'm just going to take a look at what I've got. And of course, first, we're going to choose in stock because it doesn't make much sense to look at a pack that we can't actually purchase. And what do we got? Looking at the actual data sheets for these cells and learning about, oh, look at all these specifications. But because the application that we're working on here is relatively simple and not that demanding, we're not going to pull that much current. We just want a big, dumb battery pack that lets us run our goggle battery for a long time. We don't really need to do that. What I'm going to do is I'm going to look at the milliamp hour capacity for these cells, and I'm going to pick the biggest milliamp hour capacity that I can find. This is going to be the highest energy density cell that we can get. And there's an inverse relationship between energy density, milliamp hours, and current rating. But it turns out we don't need to think about the current rating very much for this application. So here is the Samsung 50S 21700. It is a 5000 milliamp hour 25 amp battery. This has a 25 amp current rating. And how many amps is my goggle going to pull? Less than an amp, probably. Maybe 2 amps. If I really cared, I could plug my goggle into a power supply, or I could get out a multimeter and I could actually measure how many amps my goggle was pulling. It's not going to pull anywhere close to 25 amps. This cell is more than enough for the kind of applications that I'm going to be using. If I was going to be building a battery pack to run a drone, then I'd have a lot more to think about, and I probably would be choosing higher discharge packs like this 45 amp battery, 15 amp, no, 5 amp, no, 70 amp, oh, so I would probably pick that one. These batteries are going to give 70 amps. And just FYI, if you add parallel groups, then you double that number or triple that number depending on how many parallel groups you've got. So if I were to build a 6S 1P pack with these 70 amp rated batteries, I could pull 70 amps. But if I built a 6S 2P, I could pull 140 amps, etc., etc. So we're going to go with the good old Samsung 50S 5000 milliamp hour 25 amp battery. That is going to be the one that's right for us. If we wanted a little bit smaller battery pack, we could either go down to 4S 1P and get 5000 milliamp hours out of 4 individual cells, or we could go back and we could look at 18650 batteries in stock, and we could look for the largest capacity here. Here's a 3500, 8 amp. So I could build a 4S 2P. That's 2P, 3500, that's going to be 7,000 milliamp hours in a 4S 2P configuration with the 18650s. I can build, there's different ways you can slice it up to get different capacity. But I like the 4S 2P 5,000 milliamp hour Samsung S50, I think was the name of the cell. That's going to give me 10,000 milliamp hours in a 4S 2P pack. That's what I'm going to go with. So how many of these bad boys do I actually need? Well, it's 4S, that's going to be 4 in series, 2P, so I'm going to have 2 parallel groups, that's going to be 8 cells total. And I actually built 2 of these packs, so I actually purchased 16 of these. All right, so here we've got the individual 8 cells, and the next thing to do is think about the physical structure of the pack. We're going to build a 4S 2P pack, but what is that actually going to look like? And the usual way that we think about series wiring is that the negative side of one battery goes to the positive side of the other, like so. And in fact, if we connected these cells electrically like this, that would be a 2S group, a 2s group. But that's not how it's going to make the most sense. Like, this isn't some toy that we're sliding AA batteries in and we're just going to slide them in like that in a row. This is a pack. It's all going to go together. And the good news is that electrically, we can align these however makes sense, because we're just going to connect them together with wire. Well, we're not going to use wire. We're going to use nickel strips, but we can connect them any way we want. So what makes the most sense is to lay them like this. And then if they're going to be in series, we're going to take the positive and the negative, and they're going to be like this. This is going to be one series group. This is a 2s group. If I wanted to make a 3s group, I would do it like that. And you can see that we're alternating the positive and the negative side of the battery, so that when we wire them up, we'll wire this to this, and then we'll wire this to this, and then this to this, and we'll zigzag all the way around. And that's the same, you can see, if I just were to extend this out, it's the same as series wiring. We've just kind of folded it and collapsed it, and now we have a 4s group. Okay? Using that same logic, if we wanted to build parallel groups, we would take the two positive sides together and the two negative sides, and we put them together. So this is parallel, and this is series wiring. And so this would be a 2p group, and a 3p group, and a 4p group, right? And we would take one strip and put it all the way across the top, putting all of these guys in parallel, connecting all their positives and all their negatives to each other. So there is a parallel group, and here would be a series group. There you go. So if I want to build a 4s 2p battery, there's actually two different ways I can do it. I could build two different 4s groups and then put those groups in parallel with each other. So we would have 4s and then 2p. Or I could build four different 2p groups and put each of them in series with each other, and that would also give me 4s 2p. And it turns out that there is a right and a wrong way to do this. It is always better to, always may be a strong word, but this is what I've been taught. It is always better to build your parallel groups first and then put the parallel groups in series. And the exact reasons why for this go back to how electricity is flowing through the cells and flowing through the groups, and are outside the scope of anything I feel prepared to lecture on. So we're going to do it this way. We're going to build the parallel groups first, and then we're going to put the parallel groups in series. The next thing I'm going to do is I'm going to glue these cells together and lock in the physical structure of the pack. Each cell is going to be where it's going to be in the pack, period. So number one, make sure that you've got all the ends turned the right way around, the positives and negatives exactly how they're going to need to be. But number two, we need to talk about impedance matching and voltage matching. So each cell has a characteristic called the internal resistance, and I guess it's not impedance matching, it's resistance matching, whatever. It's really important that cells in a series group have as close as possible an internal resistance to each other. The reasons for that we won't dive into in this. They'll get out of balance if they don't have a very closely matching internal resistance, and you don't want that. So what you would normally do is you would buy a tool that tests internal resistance, and then you'll test the internal resistance of each cell, and like with a Sharpie, you'll write the internal resistance on the outside of the cells, and when you're done, you'll then take the cells with the closest internal resistance and you'll group them together, and that's going to be your series group. There are three reasons why we're not going to do that. The first is that these are brand new cells from the manufacturer, and their internal resistance is probably within a relatively narrow range. It still could be beneficial to do the resistance matching and get just that little bit of extra performance out of the pack, except number two, this is not a high discharge pack. Internal resistance matters most when you're discharging a lot of current. I know for a fact that's not how this pack is intended to be used. I know I'm going to be basically the only owner of this pack and never represent it as anything other than a low discharge pack, and so I'm not too worried about that. If they do get a little bit out of balance, we're going to balance charge them, so we'll put them back into balance when they're charged up. And number three, I don't have the tool to measure internal resistance. It's like an $80 tool, and I just didn't buy one for the sake of this video. So I'll put a link in the video description. There is a particular tool that's a really good value, and it would be the tool that you would use, but I'm not going to do it. So If you're in a situation where you're like recovering cells, used cells from appliances, and you're building those cells into packs, that's when it is absolutely critical to measure the internal resistance. Number one, because you can find a cell that's just damaged and bad and has a wildly out of spec internal resistance and you can throw it out. But number two, because there's going to be so much more variation in the internal resistance on used cells that have been used in the field, you're definitely going to want to match that internal resistance when you're building series groups. The other thing we need to do is we need to match the voltage. Whenever you put two cells together in parallel, if they have mismatched voltage, they will exchange current and they will equalize voltage with each other. And that current can be sometimes enough to be damaging, or you might get a spark or something. Again, we don't need to do that because these are brand new cells from the manufacturer. I did verify this with a multimeter. They're all at whatever 3.7 or 3.4 volts, whatever they ship at. And so the voltage is matched. But again, if you were dealing with cells that weren't just brand new from the manufacturer, you would want to make sure that they were at a matching voltage before you went soldering them in parallel. The next thing we're going to do is we're going to like mechanically connect these batteries together. Not electrically, but mechanically. And mechanical reinforcement is important. If we solder these together with wire or whatever, and then they're bashing around and they're moving, you can get faults that cause a fire. A wire could get nicked, a wire could come undone. We need the battery to be mechanically, structurally sound, especially if we were going to put this like on an aircraft and crash it into the ground. But even though this is just intended to kind of go in my pocket, we still want to be as safe as possible. And there's a number of ways to do this. One way that people do it is that they'll 3D print these holders and they'll put the holders on, they'll maybe glue the holder together. That's not the way we're going to do it because number one of the advantages of those 3D printed holders is that they can space the cells out slightly. And when there's a little bit of spacing between the cells, they get a little more airflow and a little more cooling, and that can help them run at higher amp loads without overheating. But this is not going to be a high amp load battery, so that's not really a consideration. We care more about like size and compactness. And the other thing is just, it can be a little tricky to find the exact 3D printed case for the exact battery you're trying to build. There's another way to do it. And the other way to do it is, ta-da, Superglue. Yes, CA. Some people use hot glue. They use a hot glue gun. Personally, I think Superglue is going to be more permanent. Maybe that's a bit negative for you. You like the fact that you could pop the batteries back out again if you use hot glue. But I've had hot glue, especially on a warm day, kind of soften and release. And I also know for a fact that Superglue is how one of the most prominent battery manufacturers in America does it. And so it's good enough for him, and it's going to be good enough for me. But if you just start gluing these together like I did on my very first pack, you will end with something janky because they're not going to be square. Maybe one of them is going to be cocked a little bit, and it's not going to be nice and neat. Instead, what I did is I printed this. And this is, frankly, not that elegant, but super effective. It is a holder. You can buy one of these on the internet for way, way, way too much money. I'll put a link to this down in the video description if you want to print it yourself. It just goes like this, and then a rubber band goes around like this, and then it kind of just holds them securely, squarely in place. By the way, I'm going to have links to all of the stuff I'm using in this video, not just the 3D print, not just this adhesive, but all of the materials and tools that you're going to see me use in the rest of the video down in the video description. They're affiliate links, so I'll get a little kickback. Well, some of them will be affiliate links. I'll get a little kickback if you use it, so it's an easy way for you to support the channel. Just go down there and click those links and do some of those are Amazon links. You can click those links anytime you shop at Amazon, and I'll get a commission on anything you buy. Anyway, so what I think I'm going to do is I think I'm just going to put a little bit of super glue here at the top. I don't want it to run down onto my workbench. Like, I don't know if you can see, it's already kind of done that in places. I don't want to make a mess. I'm just going to try and get them stuck together just the littlest bit, and then I'll finish them off outside of this little jig. I kind of don't want to move it. I guess that's the whole point. I'm going to come in from the outside, just getting some into the seam here. And then I can also go on the inside and just glue up all of these little joints. If I were really prepared, I would have some superglue accelerator, which is a material you can spritz on and it makes the superglue dry faster. Since I'm not really prepared, I'm just going to sit here and wait while the superglue dries. While that's happening, let's take a look at some other stuff that I bought for this project. This right here is nickel strip. It's going to be used instead of wire to connect the batteries to each other. One of the reasons we use nickel strip is that it is easier to spot weld instead of soldering. With wire, we would have to solder it on. The heat of the soldering iron damages the cells. And I know that we are going to do some soldering, like there are going to be some wires that we have to solder on here. But the less heat you apply to the cells, the healthier the cells are going to be. Some cells are a little more tolerant, and some cells will have their performance permanently degraded with any amount of soldering, but we want to minimize the amount of soldering that we do. Although this nickel strip might look like it has less current carrying capacity than a piece of wire, it's all about the volume, and this is fairly wide, and it's 0.15 millimeters thick, and somewhere out there's the math on how many cubic millimeters that is and how many amps it can carry. Frankly, this 0.15 millimeter is probably overkill for this pack that I'm building because this is not a high amp pack. And it's actually the limit of what my spot welder can do. If I were smarter, I might have used a calculator to do the math on how thick of a nickel strip I did. But instead, I just bought what was available from 18650 store and decided it was probably going to be good enough. These right here are ceramic tipped scissors. And the reason that we don't want metal tipped scissors is because if you're going in there with your pack with a piece of metal and you short circuit something, the sparks will come out and maybe even something worse, maybe even a fire. So we're always going to do our work with these ceramic tipped scissors. And I should also have a set of ceramic tipped tweezers, but I don't. But don't be tempted to get in there with a metal tipped tweezer and like start doing stuff, because one day the sparks will come out, and you should really just use ceramic tipped tweezers and scissors. This stuff right here is called fish paper, and it is used to protect the cells against abrasion that would cause a bad short circuit. So if we go back to the cells themselves, you can see here, I'll point with the scissors since it's safe. Here is the positive terminal of the battery, and here's the negative terminal. And it turns out that the entire side of the battery is also negative. So right here, we've got this plastic coating, probably PVC, this heat shrink coating coming right up to the edge here. But this whole lip right here is negative. So if this plastic coating weren't here and we were to lay something metal across the battery like this, it would short circuit the battery and you'd get sparks or fire. And you say, well, that's not going to happen because this plastic is here. But that plastic can wear away with abrasion, especially if we have maybe like a piece of nickel strip here and it's running between these cells, right? And so it's running across that plastic, and maybe it's kind of moving or something, and it could abrade away and cause a short circuit. So one of the things we're going to do, and in fact, we can do it now, there's no reason not to, is on all of these positive terminals, we're going to take this fish paper and we're going to put it over the top so that it provides just that little bit of extra abrasion resistance to protect against that specific failure mode. Now, you'll see people go even further than this. You'll see people build packs where they'll put fish paper in between the individual cells. They'll literally have sheets of paper in between the cells, maybe to keep other failure modes from happening. I think that's overkill for the pack that we're building today, because again, this is just designed to be a pocket pack. It's not designed to get a lot of abuse, but that's just acknowledge that that's the thing that people do. Well, I told you that we were going to spot weld these nickel strips instead of soldering them. And the reason we do that is because it creates the joint while putting much less heat into the cell, keeping the cell healthier. In order to do that, we're going to need a spot welder. And I want to tell you that probably you should not buy the exact spot welder that I bought. This is a $50, $60 spot welder. It's basically the cheapest spot welder that I could find on Amazon that claimed that it could weld a 0.15 millimeter nickel strip. And it can, but it's clearly at the limits of its capability. And you really want to make sure that your spot welds are strong and that you shouldn't be able to like easily just pull it off. And this guy is, I wouldn't trust it if I was doing like real production, or if I was really concerned about getting the absolute most safety out of my build. Nevertheless, for about 50 bucks, it will get the job done. I have to say, there is another one that's the same price that claims to be like 8,000 watts. And maybe I would buy that instead if I was really planning. But if you're really serious about this, you can get a very, very good spot welder for about 100, 140 bucks. And that's a lot more than 50 bucks or 60 bucks. So you have to decide where, but like this is like only minimally capable. And honestly, I probably should have spent more. I just couldn't bring myself to. So the way we're going to use the spot welder is we're just going to cut a set of nickel strips. We'll just cut them off. We're just going to do a demo build here, or a demo weld here. And we're going to basically turn the spot welder all the way up, which I have learned is necessary. And there's a foot pedal that will fire it. We'll put that down on the floor. And we're going to touch the piece of metal in 2 places. And then I'm going to press the button. And it's going to do its thing. And now we have created a weld. How good of a weld is it? I don't know. Let's find out. I'm just going to... Oh, we burned the paper a little. I'm just going to pull on it, and it should not pull apart very easily. Oh, that's not great. It required a little bit of force. I have a feeling if I was like actually a professional, like making batteries to sell to the public, that would be completely unacceptable strength. And that's the best this welder can do. So how do we address that? Well, one way we can address that is by just doing more welds. 1, 2, 3. Can I even do the same spot more than once? 4. I don't know. Here we go. We got more welds. Let's see if that's any stronger. Oh, yeah. That's way better. Oh, yeah, that's way better. That's not going anywhere. Oh, yeah, that's on there. Good. Okay, I'm happy about that. Next, we're going to build the parallel groups by adding nickel strips across matching sets of terminals. So here we've got 2 negative terminals, and we're going to add a nickel strip like that. 2 positive terminals, nickel strip like that. And we're going to do the same thing on the other side. And the trick that we can do to get the most out of our spot welder is to cut the strip with these scissors like this. You see, the spot welder works by pushing current from one lead down into the nickel strip and into the battery and then back up through the other lead. But if we've got this situation, a fair amount of the current is just going to flow through the nickel strip and never go down into the battery. And so it's not going to sort of cross the interface between them and create the joint. What we can do is we can cut a slit in the nickel strip like so. And likewise on the other side. And then the electricity will have a harder time flowing from here to here, right? It'll have to flow from here all the way around there, and that'll basically make more of the electricity go down into the battery and make a stronger weld. In fact, the longer we make that slit, the better this is going to work, although we don't want to compromise the mechanical integrity of the... I mean, I guess we could just have 2 parallel strips if we really wanted to. 2 completely separate parallel strips. Like cut it all the way. Well, we're not going to do that. But that is going to improve the quality of our spot welds. So here we are with our parallel groups welded together. Here's one side. And here's the other side. We now have a 2P group. A 2P group, we have 4 2P groups, but we don't have the series groups. Let's do that next. And what I want you to do is find a positive terminal at the end of the battery. Not this one here in the middle, at the very end of the battery. And I'm just going to put a plus right there. That is going to be the positive terminal for the battery as a whole. And then we're going to think about the series wiring. We're going to go from positive down to negative. So we're going to go, here's our positive. We'll put it on the side here. We're going to go positive down to this negative right here, and then across to the adjacent positive. You see? Negative, positive. Then we're going to go up through this battery, and then we're going to go over to the adjacent negative to the adjacent positive, and then down to the negative here, and over and up. And we're going to end up here at the other end of the battery, and this is going to be the negative terminal for the battery. So here's the positive terminal for the battery as a whole. Here's the negative terminal, and here is the sort of electrical flow that the series wiring is going to take us on. And if you want to, just literally draw that on there with a Sharpie, because you really don't want to screw this up. We're going to need to make these bridges right here, and right here, and right here, and that is what's going to make a 4S battery out of this pack. Okay, so here's the first bridge we need to make. We'll turn this up, and it's going to go from here to here. But where should we actually put it? In other words, should we put it here? Should we put it here? Should we put it here? I mean, you can see that electrically it doesn't matter. Like either way, we've got the same electrical connections. At first I thought maybe I should put it here in the middle so that the current will kind of flow from the cells to the center and out. But I realized that I don't want to be spot welding on top of this plastic coating, because if I burn through and melt that plastic coating, I'm going to create, well, on the negative side, it's no big deal because this whole thing is negative. But on the positive side, potentially I could burn through and create a short circuit between the nickel strip and the positive terminal and the ground. So I'm going to do it over the terminal, and I don't think it really matters whether I do it on the left or the right. We're just going to do it like so. And I'm going to do the positive terminal first so that I can make sure this is like centered up and not off center. Whereas the negative terminal, we have the whole surface of the battery to work with. Okay. Alrighty. And let's just double check our work. Here we have the positive terminal of the battery, and it goes down and across and up and across and down and across and out the negative terminal. And in fact, if we get a multimeter and we measure DC volts between the positive and the negative, we get 13.79 volts, which should be, that's a 4S voltage. Great. That means everything is correct. If you do this check and you don't get, well, it should be 4S voltage, between maybe 12 and 16 volts, depending on what voltage your cells were at. If you don't get that voltage, or you get like no voltage, then you screwed up somewhere. And we should be able to check the individual. Here is 6 volts. And on the underside, we can check 10 volts. Yeah. Here's one cell, 3.5 volts. I got my probes backward. Don't let that get to you. Here is 2 cells, 6.8 volts. There's 3 cells, 10.3 volts, and 13.7 volts. We have built a 4S2P pack. There's still more work to do. Next up, we are going to solder the XT60 lead to the battery. And I did say solder. So previously I said we don't want to solder on the cells because it can damage them. But there's just no way, well, there's some ways around it. For example, what I could have done is I could have pre-soldered the XT60 lead to this nickel strip before I spot welded the XT60, or the nickel strip, to the battery. And then the battery would never experience the heat of the soldering iron. That's a pain in the ass. What I'm going to do instead, though, is when I solder the XT60 down, I'm going to solder to the middle of the nickel strip, and that will at least somewhat reduce the amount of heat that the battery terminal itself experiences. And I'm going to use a hot soldering iron, 850 degrees Fahrenheit, whatever. Just crank it to the max it'll go so that you're in and out as fast as you can. Like, won't a hot soldering iron put more heat into the battery? Not if you're quick. You should be as quick as you can. And we could also like get some sandpaper, some abrasive. In fact, I'm pretty sure, yeah. Get some abrasive and we can like scuff this to help the solder stick better. That's good. This actually came with the nickel strip, so they knew what they were doing. And you'll also see that I have purchased a pre-made XT60 lead because I was feeling lazy, and so we're going to have to like think about the routing of the wires. So here is our positive terminal, so that's where the positive lead is going to go. And then here is our negative terminal right here, so that's where the negative lead is going to go, and you can see that's not going to give us a very long battery lead, right? But I'm okay with it. This is, again, just for sticking in my pocket and, running big goggle batteries off of, and I'm just feeling lazy today. And this is where I wish I had ceramic tweezers, because holding this with my hand is going to get hot, but I definitely, well, looking at, no, see, if I were to short circuit from here to here, this is already short-circuited on the other side. If I accidentally lay a tweezer from here to here, I will get sparks or fire. See, I'm not going to do it. I'm going to do it with my hand, but I kind of wish I had ceramic tweezers. Here we go. There we go. In and out. And what I did there was I heated the wire. Normally I would kind of try to heat the nickel strip and the wire together to get heat through the whole joint, but I'm trying to avoid heating the nickel strip as much as possible. So I heated the wire from the top and let the wire melt the puddle, and that, I think, maybe kept some of the heat out of the nickel strip. Then we come down to this end and we can see another metal utensil. Let's be real careful. We're going to cut like right about here on the negative. Strip and tin. Now that the XT60 is soldered on, I'm going to grab my battery checker and I'm going to plug it in and see if it reads correctly. This battery checker is going to be an essential part of making sure we have gotten all the wiring right. Like, I could go in with a multimeter, but then if I accidentally get the probes wrong or something, I might get it the wrong reading and think things are okay when they're not, or vice versa. But a battery checker, like, I literally just plug it into the XT60 and 13.83 volts. It didn't give me any error. It's reading correctly. That gives me confidence that everything is right. Next, I need to attach a balance lead. And once again, I have purchased a pre-made balance lead. I am not all about crimping balance leads and so forth, hand making them. And the wiring of the balance lead is a little weird if you don't like fully understand where they go. So this balance lead, the red wire is the positive wire. If you're a balance lead, sometimes a balance lead will have all colored wires and one black wire, and that's going to be the negative. Sometimes it has all like black wires and one red wire, and that's the positive. But if you look at the plug, you can see that with the little tabs up, the positive wire is all the way on the left and the negative wire is all the way on the right. So the positive wire is going to go to the positive terminal. It's going to go here. Okay. The negative wire is going to go to the negative terminal, and then the intermediate wires are going to go to each of the cells. So we're going to have one wire here, one wire here, and you can see that these are all electrically connected, so it doesn't matter where this wire goes on this right here. It could go anywhere, but one wire here, one wire here, same thing, one wire here, one wire here. And again, you can get your Sharpie and you can draw it out if you're not confident. So here is balance lead. Let's just call it 1, 2, 3, 4, 5. That's where our balance lead wires are going to go, with 1 being positive and 5 being negative. Write it down if you're not sure. And the routing of the wires is going to be a little bit tricky. So we're going to need to get to the underside, and I don't know if it makes sense to go, like sometimes you'll see them run the wire down the middle. I'm a little bit concerned that if we run the wire down the middle, maybe it will snag on the edge of this nickel strip and get cut, and so I don't want to do that. Instead, I'm just going to go down this seam here, and oh no, another nickel strip. Can I go around the outside? 2 trailer park girls go around the outside. It looks like number 2 is going to be the one that has to go the furthest. So here is 1, 2. It's the second wire, and it's going to go to here. So yeah, there we go. That's going to do it. So that routing, if I go from here to here to here, that routing does not cross any of the nickel strips, and I have enough wire left to do all the other runs. So we're going to start with the longest run so that we don't run out of wire. And again, I'm going to solder to the middle so I don't solder directly on the terminal as much as possible. And again, in and out as quickly as I can. Okay, so that wire is going to go like that to there. Not going to have much of a balance lead, are we? Oof. All right. And now that we've done that, once again, we're going to plug into the balance checker, to the cell checker, and we're going to make sure that we have a normal reading. In fact, we're going to plug the XT60 in as well so that the cell checker can sort of cross-check and make sure everything makes sense. And the cell checker is not screaming at us. And we have 3.4, 3.4, 3.4, 3.4. Everything is normal. All the cells are there and normal, and that confirms that we've got our wiring correct. Then there's just one more thing to do, and that is we're going to wrap this battery up. I think the first thing we want to do is we want to wrap it in an insulating tape like Kapton tape. Kapton, K-A-P-T-O-N. Start here like. Go all the way around, one wrap, and we want to just make sure we've got no exposed metal anywhere. It's going to get us in trouble later. While you're doing this, go make sure you like neatly route your wires. And actually, to help with the wire routing, I'm going to get a zip tie and put a zip tie around the main lead and the balance lead. Push everything into place, and yeah, that's going to help. Doesn't need to be super tight. Very carefully, not to short circuit anything. Cut that. And then once the battery is completely wrapped in Kapton tape, I put a little belt around it. Just, I don't know why I did that. It's all glued together. That doesn't need the help to hold it together, but I don't know. I just felt like the thing to do. Once you've got it completely wrapped in Kapton tape, the problem is that the Kapton tape it can split and nick very easily. So we're going to get some of this stuff. This is fabric wire harness tape, and we're going to wrap the battery in that. And it is going to provide the abrasion resistance that we need. If I were more prepared, maybe I would have some heat shrink to go on the outside. Some people will use like a bicycle inner tube. That's good. That's cool. That's not what I've got. We're just going to do it this way. And there we go. We made a battery. Oh, God. This balance lead is terrible. I will never be able to charge this without some kind of an extension because the balance lead is so short. I've really doomed myself. But that's a problem for another day, I suppose. I'm still relatively... Why did this one turn out so different? Why did this one have a longer balance lead? I don't know. Must have routed the wires differently. Well, there we go. We've made a battery, and I appreciate you coming along on the journey with me. Please tell me in the comments the things that you think I did wrong. Because like I'm legitimately interested in learning, and I'm going to forget that I asked you this, and 6 months from now, someone's going to leave a comment like, you screwed up, and I'm going to like just think you're sniping at me, and I'm going to respond, I'm going to argue with you. So, you know, be ready for that. But at least for the next few weeks, I'll remember that I asked for feedback, because I know that there's people out there who take pack building very seriously and put a lot of thought into it, and they'll know things I could have done better. So looking forward to that, and looking forward to being able to use these batteries. I will see you in the next one.